Okay. Previously, we talked about the ODE model dP/dt equals Kp, which describes the unconstrained exponential growth for the population under consideration. And of course, as we discussed at the time, generally populations don't tend to grow exponentially forever without bound because resources like space, energy, food, water, and other resources are limited. So there are some constraints. And generally, once the population, the expectation is that once the population gets large enough, the environment starts to limit further growth. Again, due to these constraints like limited space, energy, food, water. And what we want to do is that we want to develop a model that better describes this growth pattern that we should expect. That there is growth in the beginning, but at some point, because of limited resources, there will be some maximum population, and the population will not go above that. So that is the purpose of this video. We want to develop a new model that describes the population that can help us in predicting the population. And in this new model, we want to consider this like idea that this growth will not be unconstrained forever, right? At some point, there will be some limit on the growth. The growth, in a sense, depends on the population. So let me just write a summary of what I said, and then we will do the job together. The expectation is that once the population, so instead, once the population, once the population gets large enough, the environment starts to limit further growth due to constraints, due to constraints like limited space, energy, food, water, other constraints. Okay. So what is our goal? It is desirable to develop a model that better describes this growth pattern that we expect. A model that describes this growth pattern more effectively. So to be more precise, I'm looking for a model where this growth constant, K, actually depends on the population. Based on the population, P, the value of K may change. So let me write this as well. We need a model. We need a model where the growth rate K actually depends. It's not a constant. It changes with the population. Actually depends on the population. We want to allow for the possibility that K varies with P. And it can be either positive or negative, depending on the current population. That is what we're looking for. So just again, to be very, very clear, let me again write what the question is that we want to answer and carefully develop our answer to the question. So the question that we want to answer is as follows. We want to improve our model, the previous exponential growth model question. how can we account for the fact that growth rate actually depends on the population size? That is what we want to do, right? This K is not going to be a constant forever, one number forever, right? It depends on the population. If the population becomes very, very large, we want this K to be close to zero. If the population gets close to the maximum population that the environment can sustain, I want this K get close to zero. Maybe initially K is equal to that ideal K, but as the population gets bigger and bigger, we want this K gets close to zero. So that is what we want to do. And then the answer in our model, mathematically, what we should do, we should think of this K as a function of P. Answer, replace the constant K in our ODE model, the constant K in the ODE model, dP dt equals Kp, by an appropriate function of P, by a suitable function of P, an appropriate, a cleverly chosen function h of P. So instead of having a constant K, I want to have some expression in terms of P. So I want to have dP dt equals h of P, some expression in terms of P multiplied by P. So now the question is, how should we choose h of P? So now the next question for us will be, how should we choose the function h of P? What is the correct expression? What is a good expression in terms of P that I want to put inside this bracket? So let's go over the things that we want to happen. What do we want to happen here? We want what are the requirements for this h of P? We want h of P to be approximately equal to our ideal growth rate K when P of T is small, when P is small, when P of T is small. So this K is our some constant representing the growth rate in ideal condition, a constant representing the growth rate in ideal condition. When the resources are not limited, right? At least when the population is very small, we expect that those constraints do not actually exist. There is enough food, there is enough space for everyone, right? So that for P of T is small, I want this H of P to be close to the constant K. And then what else do I want from this H of P? I want H of P to decrease as P of T grows larger. H of P, we want H of P to decrease as P of T grows larger, as we discussed, right? Because of the environmental constraints. And of course, at some point, as a matter of fact, I want this growth rate to become a decay rate, right? I want H of P to be negative if the P of T is sufficiently large. I want H of P to be less than zero when P of T is sufficiently large. For example, when P of T, when P of t is greater than m, where m represents the maximum population that you can have in your environment. M is a number where m is the maximum population that the environment can sustain, based on the available resources, can sustain. Okay, there is actually a technical term for this big M. I will tell you about it later. So, but these are the expectations, right? I want to find an expression in terms of P, a function h of P that has these properties. When P is a small, there is enough resources available. When you have a small population, there is no constraint. I want h of P to be close to this ideal constant K. As P increases, I want h of P to become smaller. And at some point, this h of P becomes negative, right? The population is not going to grow forever, right? So these are the expectations. And the question is that, can I come up with a function that satisfies these properties? And I actually suggest that you stop the video, think about this a little bit, and start with simple ideas. We don't need to start with the most complex function that satisfies these properties. Can we find a simple function that satisfies these properties? And hopefully, now, after a moment's thought, you see that, as a matter of fact, there is a very simple function that has all of these properties. A simple function, let me tell you what that is. A simple function with the above properties, So I don't want to have a constant. So after not wanting a constant, the next level of complexity is a linear polynomial. And as a matter of fact, we have a linear polynomial that satisfies all these properties. With the above properties is the following linear function, is the following linear polynomial, following linear function. This is, in a sense, our simplest choice. H of P equals K, the constant K, minus P over M times K. So, folks, I want you to notice that when P is very, very small, this second term will be a small, and therefore H of P will be close to K as we wanted it to be. Notice that as P increases, this second term will become larger and larger. And so K minus a larger number, that is a smaller. H of P becomes smaller. As soon as P gets bigger than M, then the H of P will become negative. At P equals M, H of P is 0. P greater than M, H of P will be negative, which is exactly what we were looking for. So this very simple linear function will do the job for us. So what will be the resulting differential equation? The resulting differential equation, modeling the population dynamics, is dp dt equals h of p, which is, if you like, you can rewrite this as k times 1 minus p over m. K times 1 minus p over m. This is your h of p, and then multiplied by p. This h of p is replacing the role of the constant k. Now, instead of the constant k, I have this expression in terms of p, k times 1 minus p over m times p. And this equation is known for predicting the population, is known as the logistic equation. It's an improvement to the other model, to the exponential growth model, which is not realistic for long time and large populations. So the exponential growth model, this will be a better model, the logistic model. This equation is known as the logistic equation. This is another model for the population, for predicting the population, arguably better than our previous model. Okay, very, very good. And let me also introduce the like a terminology here. This K of you're familiar with. This K is called the growth constant, the growth rate. Of course, in ideal condition. Let me actually write it. K is called the growth constant in ideal condition. And then this M, in a sense, the maximum population that you can have is called the carrying capacity or saturation level. It's called the of the environment, the carrying capacity or saturation level. Which is in a sense the largest population that can be sustained by the surrounding environment. And we will see. I'm going to talk about the solution. You will see exactly how M is related to the P of T that is obtained from this model. Okay. Now, so how do we? So let me actually summarize first. So what is the consequence of this model? What is it that we need to solve in order to predict the population? We have our ODE, and also we have to equip this with an initial condition. You have to tell me what the initial population is. So here is the summary. To sum up, the logistic model gives us the following initial value problem for predicting the population. dP dt equals Kp times 1 minus P over M. The unknown is the function P of T. K and M are constants in this model. And then you have to also tell me what the initial population is, the original population is. This P naught, P of 0 equals P naught some known given number. And then if we solve this initial value problem, we will know P of T, T as a function of time. We can predict the population. Now, how can we solve this problem? As usual, we should start by solving the ODE, finding the general solution to the ODE, and then impose the initial condition. So the question is, how can I find the general solution to this ODE? Again, after a moment's thought, you will see that this ODE is a separable first order equation. This is a separable first order ODE. So you can solve this as a separable first order equation. Let me just tell you this is like an exercise for you. Let me tell you what the solutions will be. You will have constant solutions and non-constant solutions if you just focus on this ODE. Let me tell you what will happen when you just solve this ODE as a separable equation. This can be an exercise for you solving this as a separable equation. Let me start by telling you what the constant solutions will be. The constant solutions of this ODE, the constant functions that solve this ODE, the constant solutions will be P of T equals 0, the constant function 0, and P of T equals M. Just verify, plug this into the ODE, the 0 function and the constant function M, you will see that the equality holds. So what does that mean? That is the solution to the initial value problem dp dt equals kp times 1 minus p over m, p of 0 equals 0 if you start with population 0, is the constant function 0. If you start with nothing, the population will remain to be 0 in this model, which makes sense. The solution to the initial value problem dp dt equals kp times 1 minus p over m, and p of 0 equals m. If the initial population is equal to m, will be the population will remain to be m. It will not change. This is the carrying capacity of your environment. So let me actually draw these constant solutions. If you want to see a graph, here we go. This is P of t, this is t, and then here I'm telling you that this is one of your solutions. If at time t equals 0, the population is 0, it will remain to be 0. If at time t equals 0, the population is m, it will remain to be m. This is another solution. This horizontal line is a graph of a constant function. So here we have two solutions, two of the solutions. One of them, if you start with population m, one of them, if you start with population 0. Now, these are the constant solutions to our equation. But what about the non-constant solutions? So now the question is that what if P of 0 is not 0 and it's not m? So what we should do is that we should solve our separable equation, separate the variables, right? Bring everything that involves p to the left, bring everything that involves t or dt to the right, and then integrate. Again, do this as an exercise. It's a good exercise. I'm just going to tell you what you will get. Solving the initial value problem, dp dt equals kp times 1 minus p over m, and p of 0 equals p0. p0 is not 0, it's not m. So this will not be the constant solution of our equation, separable equation. The non-constant solutions gives the solution P of t. I strongly recommend that you follow the steps that we have for solving separable equations and derive this expression. P of t equals m divided by 1 plus m minus p0 divided by p0, p naught, times e to the negative kt. So this is the formula that you will get for your population as a function of time if you use the logistic model. And I hope that you immediately see that in this model. Let me just make one comment about this. Note that limit as t goes to infinity of p of t, as t goes to infinity, assuming that k is greater than 0, the initial ideal growth rate is greater than 0, as t goes to infinity, and you immediately see that this second term here, this goes to 0, because we're assuming that k is greater than 0. The growth rate in ideal condition is greater than 0. So you will get m divided by 1 plus 0, which is equal to m, right? So that the population ultimately will get closer and closer to m. So what will be the graph of this function? Let me draw some typical graphs for this the non-constant solution. And for instance, if P0 is here, your graph will look like something like this. Ultimately, it will get close to m, right? If P0 is here, your graph again will look like this. ultimately they are getting closer to n. If let's assume that we start with the initial population that is greater than m, if P0 is here, then the population will decrease to m. If you start with a population that is greater than the carrying capacity of your environment, the population will decrease, constantly decrease to, continuously decrease to m. So these are some typical solution curves for the solution that we obtain for population using the logistic model.